In the race to build ever taller skyscrapers, a hidden paradox shaped the modern skyline. Before 1949, no tower could rise safely above 400 feet, as cranes themselves became prisoners of gravity and human risk. Then, a single German invention unlocked something extraordinary: tower cranes that could climb, disassemble, and rebuild themselves, unlocking ambitions from post-war Europe to Dubai's futuristic horizon. But how did engineering a machine to build itself rewrite the limits of cities and the dangers faced by those who run them? This is the story that How Tower Cranes Build Themselves, Engineering Skyward Ambition, sets out to reveal. Before the age of hydraulic ingenuity, the tallest ambitions of builders ran into a hard stop at 400 feet. The reason was not just the limits of steel or concrete, but the limits of the cranes themselves. Each additional story meant workers had to climb rickety ladders, hauling tools and steel pins by hand, exposed to wind and gravity. Dismantling a crane at height required the same perilous climb, often repeated every 100 feet. The risks were constant. One slip, one poorly secured bolt, and lives were lost. For decades, this ceiling defined the skyline of every major city. In the ruins of post-war Germany, a new approach took shape. In 1949, Hans Liebherr introduced the TK-10, a mobile tower crane that would become the prototype for a new generation. Its secret was hydraulic self-jacking, a system of rams that could lift the crane's upper structure by 10 feet at a time, allowing workers to insert a new mast section beneath. Instead of taking the crane apart piece by piece, the machine could now raise itself, one controlled leap after another. Each lift was a small revolution, completed in minutes rather than days, and with the operator and cab remaining safely above the chaos of the site below. The first climbs were tense, every movement amplified by the creaks of steel and the hiss of hydraulics. But the system worked. Tolerances held, accidents dropped, and the 400-foot barrier was broken. The TK-10 soon spread from German reconstruction sites to the rebuilding of cities across Europe. Its influence reached as far as Australia, where engineers began experimenting with internal support systems to further reduce sway and speed up assembly. By the early 1960s, the idea of a crane that could climb with its building was no longer a fantasy. It was an essential tool for shaping the modern cityscape. How did those early risks and breakthroughs change the way builders saw the sky? For many, the answer was simple. The horizon was no longer a limit, but a challenge waiting for the next invention. By the early 1970s, another transformation swept through the world of tower cranes. Where hydraulics had once driven the climb, electric drive systems began taking over the heavy lifting. The change started quietly, with manufacturers like Petronas in France and Liebherr in Germany introducing electric motors for hoisting, slewing, and trolleying. These new drives replaced pumps and pressurized fluid with direct coupled motors, machines that could run for hours without overheating or leaking a drop of oil. The numbers told the story. Electric cranes used up to 40% less energy per ton lifted than their hydraulic predecessors. For a high-rise site running all day, this meant energy consumption dropped from nearly 3 kilowatt-hours per ton to under 2. Maintenance crews spent less time chasing leaks and more time keeping projects on schedule. Over a year, the savings added up, not just in fuel costs, but in fewer breakdowns and less downtime. Operators noticed the difference right away. Electric controls made each movement smoother and more precise. A load could be stopped and held within millimeters, even in gusty conditions. Regenerative braking, a feature borrowed from electric trains. The crane to recover energy during load descent, making each lift not just safer, but smarter. In-cab controls responded instantly, giving operators a new level of confidence and control. Within a decade, electric drive had become the standard for most new tower cranes in Europe and North America. By 1980, More than 80% of models sold in these regions used electric power for their main motions. Hydraulics remained for climbing mechanisms, but the era of fluid-filled lines and constant repairs was fading. This leap in efficiency didn't just save energy, it set the stage for modern construction's relentless pace. With quieter, cleaner, and more reliable cranes, builders could reach higher, work faster, and push the boundaries of what a city skyline could be. The foundation for the next generation of engineering was now set in steel and powered by the quiet hum of electricity. How did the switch to electric drives change the way your teams worked? Beneath every tower crane, the story begins with a foundation that few ever see. A slab of concrete, weighing nearly 400 tons, is poured and reinforced with a dense lattice of steel rebar. Its job is simple in theory, but immense in practice. Hold firm against the twisting force of up to 100,000 foot-pounds as the crane swings and climbs above. The concrete mix is calibrated for strength and flow, with aggregates and admixtures chosen to minimize shrinkage and resist cracking. Once poured, the base is left to cure for 28 days. No exceptions. During that month, inspectors arrive with ultrasonic scanners, searching for hidden voids or honeycombing that could spell disaster later on. On a cold morning, a rigging supervisor stands over the site, clipboard in hand. He checks the curing logs and the results of every test. OSHA protocols demand a meticulous record: moisture levels, ambient temperature, even the torque applied to each anchor bolt. Only when the foundation passes every inspection does the next phase begin. Mobile cranes roll in, unloading the first mast sections, each one a lattice of high-tensile steel, precision drilled for perfect alignment. Workers bolt the base plates to embedded anchors, tightening to specified torque values that will hold for the life of the project. Laser levels and plumb lines guide each segment, ensuring the verticality of the mast within a margin of just 1/16 of an inch. The teamwork here is silent but exacting. Riggers signaling, surveyors adjusting, supervisors double-checking every measurement. If a single bolt is missed or a pocket of air is trapped in the concrete, the entire structure is at risk. Only when the base is certified and the first steel stands true does the crane earn the right to climb. What stories do veteran riggers tell about the toughest foundations they ever built? For some, it's the memory of a winter pour that nearly froze solid, or a last-minute save when a void was caught, just in time. For all, the foundation is more than concrete. It's the promise that everything above will hold, no matter how high the ambition reaches. A self-climbing tower crane's ascent is a carefully orchestrated cycle of hydraulics, sensors, and precise engineering. The process begins with hydraulic rams, each one capable of lifting more than 150 tons, pressing upward to raise the entire upper works, operator cab, jib, and counterweights by 20 feet in a single movement. This is not a rough jolt, but a slow, measured climb, taking about 30 minutes from start to finish. Every step is monitored by load cells, which measure the exact weight and balance of the crane as it rises. These sensors feed real-time data to the control system, ensuring that alignment stays within 1/16 of an inch, no wider than the edge of a credit card. Engineers oversee the operation from a control panel, watching for any sign of deviation. If the load cells detect forces exceeding the preset limit, just 5% above the calculated safe load, the system triggers an automatic stop, locking the rams and halting the climb. This auto-abort function is a silent guardian, preventing overloading or misalignment before it can threaten the structure. As the upper works reach their new height, the climbing frame holds the load in place while workers guide a new mast section into the gap. Guide rollers and alignment pins ensure the section fits perfectly, with bolts torqued to specification. Counterweights, sometimes weighing up to 100 tons, are shifted as needed to maintain the crane's balance, keeping the moment arm within strict limits. After each climb, engineers perform a balance check, aiming for a maximum wobble of 0.3 degrees, less than the tilt of a glass of water on a table. This choreography repeats every week or two as the building grows, with each lift relying on a blend of mechanical power and digital oversight. The safeguards and redundancies built into the system are invisible to most, but for the engineers and operators, they are the difference between routine progress and disaster. What aspect of this precision would you trust most if you were in the operator's seat? Inside the cab, the world narrows to a rectangle of glass and steel, suspended hundreds of feet above the ground. Each climb starts with the low groan of hydraulics and the slow, deliberate lift of the entire upper works. The cab sways, not wildly, but with a steady rhythm, sometimes up to 2 feet side to side when the wind picks up. Operators learn to read the subtle cues: a shift in the seat, the creak of a joint, the faint vibration underfoot. It's a sensation that never fully disappears, even after years on the job. The first solo shift at height is a test of nerve. Some describe the feeling as a cold rush, others as a calm focus that settles in once the climb begins. At 400 feet, with the city stretched below, the isolation becomes real. There are hours when the only voices come through a radio, and every decision, every stop, every lift, carries the weight of lives and millions of dollars in steel. For many, the cab becomes both a sanctuary and a cell. 8 to 12 hours alone, day after day, shapes a certain mindset. Some operators admit to moments of anxiety or fatigue, especially during long stretches of bad weather. The rewards are tangible. Experienced crane operators on major projects earn between $80,000 and $150,000 a year. The pay reflects the risk, the responsibility, and the rare skill set required to keep a project moving skyward. But the cost is more than physical. Surveys find that over half of operators report chronic back or neck pain, and many quietly deal with stress or trouble sleeping. The job demands focus, resilience, and a willingness to accept solitude as part of the deal. What keeps operators coming back is a sense of pride, knowing that each lift, each careful adjustment, pushes the skyline a little higher. Yet every ascent serves as a reminder: up here, there is no room for error, and every choice matters. At heights above 200 feet, a tower crane's survival depends on more than its own strength. Steel tie-ins, known as collars or clamp beams, connect the mast directly to the building's frame. These connections aren't just extra insurance. They're responsible for absorbing up to 70% of the wind's lateral force. Without them, a sudden gust could turn the entire crane into a lever, threatening collapse. Each tie-in is engineered and installed with precision, following a schedule that matches the building's rise. Before a lower tie is removed, the one above must be fully secured and tested, leaving only a brief window, usually 45 to 60 minutes, when the crane stands with just a single anchor point. During this exposed interval, every eye is on the anemometer. If wind speeds hit 25 miles per hour, work stops immediately, no exceptions. On a spring afternoon in Chicago, a rigger supervisor recalls the tension as a storm front rolled in during one of these intervals. Lightning flickered on the horizon. The operator, watching the wind gauge, called down to the ground, "We're holding at 22. If it jumps, we're out." For nearly an hour, the crew waited, tools in hand, as the building and crane swayed together. The tie-in finally locked just as rain began to fall, the storm passing with the crane still upright and secure. These moments reveal the partnership between machine and building, a shared defense against nature's unpredictability. Every tie-in is a handshake of steel and concrete, a promise that the crane and the structure will rise and survive together. What wind or weather events tested your crew's nerves the most? On a March morning in 2008, 7 workers lost their lives when a tower crane collapsed in New York City. Investigators traced the disaster to a failed tie-in sequence. One crucial connection between the mast and the building was missing. Wind loaded the exposed crane, and the structure buckled in seconds. The alarms had sounded at 105% of rated load. But by then, the margin for error had vanished. Survivors described the chaos as the mast twisted, steel shrieked, and the upperworks plunged to the street below. In the aftermath, city officials rewrote inspection protocols, mandating real-time monitoring during every exposed interval and requiring engineers to sign off on each tie-in before work resumed. Halfway across the world, in Dubai 2015, a different kind of crisis unfolded. A trolley seized mid-jump, locking the load carriage in place just as the climbing frame was being extended. Sensors flagged a drift in balance, and the system auto-aborted. On the ground, the rigging supervisor called for a manual release, an emergency maneuver that would let the trolley move free, but only if the crew could synchronize their actions. The lead engineer, recalling the 2008 tragedy, insisted on a step-by-step confirmation over the radio. Workers climbed the mast, torqued the release bolts by hand, and watched as the load settled back into alignment. The crane held. No one was injured, but the lesson was clear. Even with advanced sensors and strict protocols, human vigilance remains the last line of defense. Industry data shows that nearly a third of crane incidents still involve human error. Misread gauges, rushed procedures, assumptions made under pressure. The stakes are measured in seconds, but the consequences last for years. Every rigger and engineer who has faced a near miss remembers the sound of alarms, the quick calculations, and the silent hope that training will be enough. What skills or decisions saved your crew when the margin grew razor thin? A new generation of tower cranes is redefining what cities can build, and how fast. The economics alone are striking. Modern self-climbing cranes, equipped with electric drives and digital monitoring, have trimmed millions from the cost of a single skyscraper. Faster assembly, reduced labor hours, and fewer equipment rentals mean projects that once took years now rise in months. On some of the world's largest towers, these savings can reach into the millions, not just in direct costs, but in the value of opening a building ahead of schedule. Sustainability shapes every new design. Electric hydraulics now cut site emissions by nearly a third compared to diesel-powered predecessors. In Asia, bamboo scaffolding, still common in mid-rise construction, once sliced project costs by as much as 30%, a testament to the ingenuity of adapting local materials. While today's high-rise cranes rely on high-tensile steel for strength, the spirit of adaptation persists. Engineers continually search for lighter, stronger, and greener materials to push the limits of height and efficiency. At the leading edge, projects like Jeddah Tower in Saudi Arabia are forcing a rethink of the crane itself. To reach a kilometer into the sky, engineers are developing custom-built machines with triple tie-ins, sensor arrays, and wind compensation systems that can respond to shifting gusts in real time. The ambition is not just to climb higher, but to do so safely, sustainably, and with precision measured in fractions of a degree. Artificial intelligence is beginning to play a role, adjusting crane movements for wind and load in ways no human could calculate, moment to moment. Operators now work alongside predictive systems that monitor every bolt, bearing, and cable, reducing the risk of error and allowing for more daring designs. The lessons of bamboo scaffolding, hydraulic leaps, and digital controls all converge here, each breakthrough building on the last, each innovation a step toward the next horizon. How far can technology take us before the sky itself becomes the only boundary? Since the 1949 debut of Hans Liebherr's hydraulic self-jacking crane, The limit of 400 feet on high-rise construction has been erased, enabling cities like New York and Dubai to reach new heights. Tower cranes now anchor themselves with 400-ton foundations, rise 20 feet at a time with tolerances of 1/16 inch, and rely on sensors that stop operations at just 5% overload. Yet questions remain. Not all near misses are publicly documented, and some mechanical failures, like the 2015 Dubai case, still leave gaps in official records. What is certain is that each safety reform, from OSHA's rigorous inspections to AI-driven controls, has reduced fatalities by 60% since the 1970s. Today, as electric hydraulics cut emissions and engineers prepare for towers over 1,000 meters, the core principle holds. Progress is measured by both ambition and vigilance. The story of self-building cranes is not only one of engineering, but of ongoing accountability, proving that every skyline is built on lessons learned, risks managed, and lives protected.